Hi guys, welcome back to my channel. Today we'll be doing another crazy integral. And the fun fact is this integral comes up uh, during condensed matter physics. And like the last video, even this is going to be like a long journey. So guys, please be patient and let's get to it. So we have our integral I is equal to the integral from negative infinity to infinity of x squared over 1 plus e to the negative x times 1 plus e to the x dx. So our interval of our limits of integration are from minus infinity to infinity. We could try to use exploit symmetry, but before that we need to check if this is like an odd function or like an even function. So let's call our integrand f of x, which is x squared over 1 plus e to the negative x times 1 plus e to the x dx. And let's plug in negative x instead of x now. Negative x squared is x squared again. 1 plus e to the x times 1 plus e to the minus x. So, so f of x is equal to f of negative x, right? So the function is even. So we can convert our integral now as 2 times the integral from 0 to infinity. So half of the interval. Twice of integral over half the interval of x squared over 1 plus e to the x times 1 plus e to the negative x dx. Now one thing that we can do is convert this negative exponent into like a positive exponent. So 2 times the integral from negative infinity, 0 to infinity of x squared over 1 plus e to the x, then times 1 plus 1 over e to the x. So I converted a negative exponent into like a positive exponent. And now this denominator gets multiplied in the numerator. So 0 to infinity of e raised to x times x squared. And in the denominator we have 1 plus e raised to x, and then when we cross multiply we have e raised to x plus 1. So it's essentially e raised to x plus 1 the whole thing squared dx, right? And now I'm going to persist still, and I'm going to be integrating by parts. So let's do that now. So this was our original integral, and now let's ask ourselves, what should we differentiate and what should we integrate? Well, one way to think about uh, the integrand here is, well, we have an x squared, right? We have like a polynomial term, and differentiating that eventually, so since it's x squared, so we differentiate like twice, we'll eventually end up with 0, and that will uh, tend to ease things up a bit. So let's do our standard DI method. So we want to differentiate x squared, right? So we'll have to integrate the other bit, x e raised to x upon 1 plus e raised to x, the whole thing squared. When I differentiate this, I simply get a 2x, and I have to integrate this now to find a suitable antiderivative. So let's do that on another page. So antiderivative of e raised to x over 1 plus e raised to x, the whole thing squared dx. You might have guessed we could do a u substitution. U is equal to e raised to x plus 1, and so du is therefore e raised to x dx. We have everything in place. So du upon u squared, which evaluates to 1 over negative 1 over u, and u is nothing but e raised to x plus 1. Let's just not write the constant for now, because eventually we'll have to just plug in the bounds. So 1 over 1 plus e raised to x. And now I'll have to differentiate this again. So I have 2, and then I'll have to integrate this. So let's do that on another page maybe. So I have to integrate negative 1 over 1 plus e raised to x dx. So one thing that we can do now is multiply and divide by e raised to negative x, because if we do that in the denominator we have e raised to negative x, and then e raised to negative x times e raised to x is just 1. So, and now we can introduce another substitution. Let w equals e raised to negative x plus 1. So dw is naturally minus e raised to minus x dx, and we have everything in place. So this becomes dw over w, and that evaluates to the natural log of w, and w is e raised to minus x plus 1. As I said, let's not write the constants now. This is ln natural log of 1 plus e raised to negative x. Well, now integrating this is a big pain. So, instead of finding the antiderivative and, because eventually we're getting 0 this side, I'll just like to do it this way. So, this times this, you have adding, and then we have a subtraction when we multiply this in there. So, minus here. And then instead of finding the antiderivative, I said, let's just plug this 2 and this thing together in an integral in the end. That's how our integration by parts works. So we had a 2 outside initially, and then we had all this junk. So minus x squared over 1 plus e raised to x. But remember, we have to evaluate it from 0 to infinity, and then the subtraction there was minus 2x times natural log of 1 plus e raised to negative x, again evaluated from infinity to 0. And then I said, let's adjacent terms, we'll just put them inside an integral. So plus the definite integral from 0 to infinity of 2 times the natural log of 1 plus e raised to minus x dx. So let's go ahead and evaluate these functions at infinity and then at 0. So at infinity, well, the denominator is going to be way large than is going to grow way larger than the numerator. So you can say that the denominator will approach infinity quicker. So this thing will just go to 0, and then when you plug in 0, we have 1 plus e raised to 0, which is 2 in the denominator, and then in the numerator we just have a 0. So everything in both the cases, this thing will just go to 0. Now this might seem slightly complicated for the infinity case, so let's just do it properly. So basically we have let's write in terms of limits. The limit as x approaches infinity of 2x times the natural log of 1 plus e raised to negative x. Now you might remember some properties of natural logs, because like you have, when x approaches infinity, you have e raised to negative x that's approaching 0. So that might remind you of this property of logarithms. So limit as h approaches 0 of natural log of 1 plus h over h is just 1. So we might want to divide by an e raised to negative x here. So natural log of 1 plus e raised to negative x over e raised to negative x, and then we'll have to still multiply. So another separate limit as x approaches infinity of e raised to negative x times 2x. So well, you might just want to change some limits, or if you can see it, it's great. So as x approaches infinity, e raised to negative x approaches 0, and that happens in the numerator and the denominator, and which is exactly like this form that we had. So all of this is just going to disappear into a 1. 1 multiplied with this limit is just this limit. So this limit as x approaches infinity of 2x over e raised to x. So we have an infinity over infinity situation here. So let's just go ahead and apply L'Hopital's rule. So we have the limit as x approaches infinity of 2 over e raised to x, and as e raised to x approaches infinity, when x approaches infinity, this entire thing will just go to 0. Well, so for the infinity case, this is going to 0, and then even for the 0 case, because of this x, I mean, it's almost like thanks to this x, the entire term is going to 0. So 0 both the times. And therefore all we are left with is this nasty integral that I could not find an antiderivative easily for. So we have 2 into 2, so we have a 4 times the integral from 0 to infinity of the natural log of 1 plus e raised to negative x dx. Let's do it on a separate page. 4 times the integral from 0 to infinity of the natural log of 1 plus e raised to negative x dx. So looks like we can't do anything more with the integrand. So anything more in terms of elementary techniques. So what we can do is we can try to introduce the Taylor series for the natural log. So if you remember my last video, so the Taylor series of say 1 plus x was summation from n equals 1 to infinity of minus 1 raised to n plus 1 times x raised to n all over n. But instead of x, now we have e raised to negative x. So we just make those changes accordingly. So sum from n equals 1 to infinity minus 1 to the n plus 1 power, then e raised to negative nx over n. Now we just have to integrate this, right? So you can see integrating both sides from 0 to infinity. So we can totally interchange the sums and integrals. So we just have the sum from n equals 1 to infinity 1 over n, and we have a negative 1 raised to n plus 1 on top, times the integral from 0 to infinity of e raised to negative nx dx. Well, okay, so let's integrate this, and integrating this shouldn't be a hard job. So we have a negative, and we have e raised to negative nx over n, but evaluated from infinity to 0. So we have sum from n equals 1 to infinity. I can club the n's together. So I have minus 1 raised to n plus 1 over n squared, and don't forget the negative. And well, e raised to negative infinity is just 0, and e raised to 0 is a positive 1. So in all, we had a negative 1 here, and then that negative 1 just gets multiplied by this negative, rendering it positive. So finally, all we are left with is this infinite sum, minus 1 raised to n plus 1 over n squared. But this is just our integral from 0 to infinity of the natural log of 1 plus e raised to negative x. We need 4 of those, right? So we should have multiplied 4 from the start. We have a 4 here. Yeah, 4. Now let's remember what this is. It's nothing but the Dirichlet eta function at 2. Because let me remind you again, the Dirichlet eta of S, for example, is the sum as n equals 1 to infinity of minus 1 to the nth plus 1 power over n to the s power. Now how do we find the Dirichlet eta of 2? Well, there was this beautiful relation that Dirichlet eta of s is equal to 1 minus 2 raised to 1 minus s times the Riemann zeta of s. So, instead of s, we can just plug in 2 now. We have 1 minus 2 is a negative 2, 2 raised to negative, 1 minus 2 is negative 1, 2 raised to negative 1 is just a half, and we have the Riemann zeta of 2. 1 minus half is a half. Riemann zeta of 2, and let me remind you what that is. It's the sum as n equals 1 to infinity of 1 over n squared. So it's the inverse square series, and that, because of Euler, is pi squared over 6, and then we have a half, so pi squared over 12. But that's just the Riemann zeta of 2, right? And we have 4 of those. So it's 4 of Riemann zeta of 2, which is nothing but 4 times pi squared over 12, which evaluates finally to pi squared over 3. There's beautiful relation, and the pi just comes in out of nowhere thanks to this inverse square series. So thanks for this video, guys. Thanks for watching this video, guys. And if you like it, please click the like button, share, subscribe, and have a great day.